Okay, great. Well, yeah, thank you very much for attending, everyone. And I'd like to welcome you. Get two speakers for the price of one today. So really pleased to have um, speakers here, Pierre Emmanuel and Valerio from Primis AI. Sounds like they're doing some really exciting stuff, and thank you very much to Andrew for drawing that to the attention of the spatial ML community. So we'd really like to hear more about this, and delighted to have you here. Please tell us.
Sounds good. Thank you so much, George. So a special thank you to George and Andrew for inviting us today. It's a great pleasure to present the work we've been doing at Primis along the path of fully automating the generation of RTL from language to RTL, and especially using agentic technologies that have built-in verification in the loop. I'm going to first kick off by giving a short presentation about what we're up to at Primis, and then Valerio, our CTO, will continue with a more detailed conversation on the actual techniques within the agentic workflow. So at Primis, we're really shooting towards full workplace automation with an initial spin around EDA, which is our forte. And you might have heard about Primis AI with the introduction of RapidGPT back in 2023, which was the first copilot for hardware design. Now, there are many copilots. Copilots became a mundane technology in the AI world, even though RapidGPT is still the prime and most used copilot for hardware design today. We migrated our technology to AI agentic systems, where you can see on these illustrated pictures that we're really shooting for simply having AI helping the designer into having AI becoming a fundamental part of your design team. And what do we mean by that? Valerie, if you can go to the next slide. It's actually creating systems, workflows that are based on multi-agentic behavior, where design teams can capture their tribal knowledge, they can capture their ways of working, and automate most of their workflows. This is an illustration here of a typical workflow we have in our product line called Magnus and Inspitio. Magnus is a tool for front-end designer, and Inspitio is for designer verification, where you can see that the operators start with some high-level specifications and then can offload all the design tasks to this multi-agent system where you'll have a combination of agents working together alongside more traditional technologies such as EDA tools, right, that can be directly called from the agentic solution. This is fundamental to pair the deterministic behavior of EDA alongside the creative behavior of Gen AI, and that's what we will see today is a big boost in terms of accuracy and performance, but as well grouping all the internal knowledge of companies, all their reference methodologies, all their prior designs, all of that happening within our customers' networks, and us never having access to this data. So all in all, right, the idea is that having these multi-agent systems will help automating tasks such as the creation, in that case, of a system into a fully verified RTL. So now each of the agents we are having in this workflow is based on several technologies we built that were made to increase the cognitive capabilities of the agents. Everything started, of course, with baseline LLMs. We started creating that, a long time ago, even prior ChatGPT came out. But we very quickly realized that while LLMs will be fantastic natural language processors, we had to pair them with more technologies to first make them EDA domain specific. That's a technology we call the Primis AI Domain Adapt, where now our LLMs, our agents are fully hardware design capable. And then we paired that with an advanced RAG pipeline. We call that Primis DKA for dynamic knowledge augmentation, where You can retrieve code, knowledge, specifications, reference methodologies. You can really navigate within knowledge of designers and inter company data. Then we have added another technology. We call that Primis AI Auto EDA that allows for execution of EDA tools and then getting reports and interacting and reacting to results of more traditional EDA technologies. Also working on different additional technologies to monitor activities and to persist in learning within an actual agent. But that will come for the future. What you can see here, though, is that each of our agents are pretty capable by grouping the power of traditional EDA alongside Gen AI in what we call generative EDA. With that, I will let Valerio take over and tell you more about specifically the AI real workflow that he designed for RTL driven verification driven RTL generation. Valerio, the floor is yours.
Thank you. Thank you very much. So I would like to start with assessing some of the risks of AI, just to introduce the topic. So risks of AI, of course, is a broad topic by itself. So I'm not necessarily referring to some of the news that we have seen recently, because, LLMs were niche until, a few years ago. But since the explosion that we saw with RapidGPT, with ChatGPT, you can see and hear discussion about LLMs, even when you do grocery and stuff like that. So what I actually wanted to discuss here is more things that are more tangible, like problems that we see nowadays. So all these things are for real and will happen probably. But what happens right now is something that we can always basically witness every day while using LLMs as a users. And I'm referring to the story of two lawyers that were questioned about a memoir that they wrote to defend their clients. Basically, what happens is that the court was just puzzled about the other cases that were cited inside their memoir. So they asked, so we cannot find these previous cases in our archive, so please tell us what happened. And basically, it turns out that these lawyers use ChatGPT to generate the memoir, just to speed up things. It makes sense because, you use generative languages, generative models, just to speed up your usual workflow. The problem is that when they were questioned about these mistakes, they just claimed that, yes, we use this software, but we just never thought that it could made up information. So if you think about it, this is quite a big paradigm shift, because prior to that, we were used to use computers to just double check our information. From this moment on, we just need to double check what the computer is telling us. So hallucinations are becoming relevant, very relevant nowadays. They are with the increasing in the pervasiveness of LLMs, is even more important to have and double check all the information that are coming from LLMs. So this is part of the motivation. Of course, these problems are even more relevant when we talk about programming languages, in particular RTL languages in our case. As I said, LLMs are transforming basically all aspects of our everyday life, and RTL design and hardware design in general is no exception. And these challenges are even more relevant in a zero-shot prompting setting. So what does it mean, zero-shot? Is basically when you just provide a single prompt and you expect to have the complete solution, which is unlikely, because what happens most of the time is that you need to set the ground first, what you want to accomplish, and then provide some fine-grained instructions to just guide the LLM to do what it wants to do. So at the beginning, especially, so when multiple LLMs were made public, either open source or closed source, um, the rate of syntax mistakes in code were quite significant, with reports saying that almost 46% of all the pieces of code that were generated by ChatGPT, the first version that came out 2 years ago, were syntactically incorrect. And the probabilistic nature of LLMs is what leads to inconsistent results as well, because maybe you can get some good answer, you repeat the same prompt a couple of times, and maybe you are not able to replicate the good answer that you received first. So what happens with the rise of LLMs that many companies are trying to move towards this new paradigm, including some big corporations. However, the problem is that you need to double check everything, as we said before. So this means that instead of speeding up the process, the workflow that you are already used to, because you use the same workflow since 10, 20 years, so you have to include and increase debugging workload because you have to double check every single thing that the LLM produces. So this was the main motivation behind the idea of introducing some kind of self-verifying RTL code generation technique. In this case, multi-agent. Multi-agent because one of the first problem is that usually zero shot doesn't work that well with complex tasks. So you need to split that. But asking the user to do that is not that not that much of a choice, because if you want to do something that is consistent, then you have to have a system that does that for you. And we wanted to leverage EDA tools because the objective was, let's try to replicate what the usual human-like behavior is. So human will just write a piece of code and verify it, simulate, make sure that everything is as expected. So we wanted to replicate this kind of behavior. And this kind of behavior has a specific name that goes under the name of reasoning plus acting. So the REACT paradigm. We see here on the picture, it does entail at least two entities. So you have to have an LLM and the surrounding environment. The point is, having LLMs just carrying out a chain of thought process by themselves is not really something that can be exploited every time, because if an LLM does only rely on itself, it will likely diverge if mistakes are introduced in the chain of thought. So the point is, okay, let's try to leverage something that is outside of the LLM, like in this case, the surrounding environment. In the React paradigm, you have the first step, which is the self chain of thought prompting. So the LLM tries to break the task into multiple subtasks and try to understand what is the flow that it has to follow. The second part is the action, like you see here. So the LLM does actually send some input to another agent, for instance, or it can be a database, for instance, if you use a RAG system, or it can be a simulator. And this other entity will just produce you some observations. And this observation will then be used by the LLM to just correct the chain of thought or refine the thinking and carry out the job, hopefully in the right way. So the idea is that by using this kind of interaction between the LLM and the surrounding environment, you can actually reduce the errors. So this was at the foundation of the idea behind ARIL. So ARIL is an AI-based code generation that does leverage that leverages verification in the loop automatically. And what you see here is the architectural overview. So as you see, it does follow a React kind of implementation. So you have three agents: the code agent, the review agent, and the verification agent. From the environment, you have the compiler, let's call it compiler, the simulator, and the feedback are represented with the output of this compiler and simulator, essentially, that are fed back to the agents in order to refine their chain of thought process. Let's focus on the first part. So I haven't mentioned that also the user is part of the environment. Indeed, in many cases, when you have a complex task that you want to resolve via LLM, usually what I saw is that most of the times you will just write something that is very simple for a complex task and expect that to be enough. Unfortunately, it's not the case. So part of the chain of thought process is to force the LLM to understand the requirements first. If they are not clear enough, it should ask the users for follow-up questions. This is part of the prompt analysis, and it's probably the most important part because that will lead all the subsequent tasks that are part of the workflow itself. The code agent as well does generate a test bench out of these specifications, and it will leverage the review and verification agents to just make sure that feedback is relevant to that specific design and not just made up and the product of multiple hallucinations. So if we could inspect a little bit what happens inside this code agent memory, let's say, we will see that once you receive the generated the query from the user, it will just start processing the request. This is an example of an example prompt, and will just interact with the other tools. So in this case, you start with the test bench and RTL design. The code is first passed to the compiler, and the error logs are then processed by the review agent. What happens here is that the review agent will extract all the information and will rework these logs as corrective prompts, which basically means for each and every mistake that happened, it will just translate that error message in the log into something that is more meaningful, like, for instance, adding the line where the error occurred, maybe some pieces of code that are surrounding the specific error, or try to instruct a little bit better the code agent on where the error actually occurred. Again, if we could, just inspect a little bit the memory of the review agent, this is what we will see. So basically, it's like zooming into the template that can be used for this type of agents. So you have the original RTL code, the compiler logs, and then you have the corrective prompts that are generated by the review agent during the chain of thought. And then the last step is the functional optimization loop. So where we basically start with valid test bench and candidate RTL, and the simulation happens to just make sure that the functionality of the RTL is the one that the user is expecting to see. Again, similarly to the previous case, the simulation logs are generated during the simulation and are analyzed by the verification agent, pretty much similar to what we saw with the review agent, such that corrective prompts are generated then by the verification agent and fed back to the code agent again, and then the loop starts again. Again, you have to syntax check first, because you never know about potential errors introduced at each step where the code agent does introduce additional lines of code. or does modify the previous ones. And so the loops repeats until the completion. So the key features, so as we said, two main stages. So the syntax check, which is controlled by the review agent and does guarantee that the RTL is syntactically correct. And the functional optimization loop, which does ensure that the functionality of the RTL is the one that the user is actually expecting. Three agents, code, verification, and the review ones can be implemented in different ways, of course. So the idea is that it doesn't make much sense to, probably doesn't make much sense to just leverage some specific fine-tuned model for each and every agent. So you can interchange LLMs inside each agent, depending on the quality that you expect to have, or the model that works best for your specific use case. And you can also extend this kind of framework to different scenarios. Like, for instance, you could also carry out some other programming languages tasks or anything like that that needs to be verified and simulated. The way we designed that was also to be language agnostic. So not only LLM agnostic, but also language agnostic, just to make sure that we cover most of the cases entailed in hardware design, essentially. And again, using general purpose LLMs is much more advantageous in this case, because training is probably too difficult to do in most cases, in most scenarios. So it makes sense that you leverage the chain of thought process, which is better than just fine-tuning some very large and complex LLMs. So the experimental results of Avril. So we decided to take the Verilog Eval Human benchmark suite, which is composed of 156 benchmarks. The tool that we use for the simulation, the compile process was without the design suite. For mixed language, because we also target VHDL besides Verilog. And for the metrics, we just take into account the passive one, and we differentiate between the syntax and the functional one. For the syntax, it just indicates the percentage of the design that are syntactically correct. So basically, based on a cohort of, for instance, 5 different answers generated out of a prompt, you select one random answer and you check that specific piece of code for syntactical errors. That will give you the passive one. Same thing for the functional, but in this case, we take into account the functionality. So we use the test bench. In this case, to evaluate the passive one, we actually use the test bench from the benchmark suite, not the one that was automatically generated, which is only used for the internal process. And we also analyze the latency, because it makes sense that you also assess how longer it takes for the LLM to produce a meaningful result. So code quality for Verilog. So on the left, you have the syntax passive one. On the right, you have the functional passive one. In both cases, on the bottom, you have the different models that are taken into account. So we selected Llama 3 in the 70B version, GPT-4o, and Claude 3.5 Sonnet. The lighter bar here means the baseline model. So just API call to the specific model, or for a Llama 3 version, for instance, it was ran locally via Llama. And on the darker bar, you have the Avril framework with that specific model. So for instance, this bar here is Avril plus Llama 3. So all the agents were implemented with Llama 3. Same thing for GPT-O Claude 3.5. For Verilog, things are much easier because we were able to just achieve 100% accuracy, let's call it accuracy, among all the 156 benchmarks. However, for the functional part, it is a little bit more challenging because sometimes happens that the models are not able to actually fix all the issues that are present in the first attempt. And what happens is that they will just diverge again, in the multiple loops that entail the process, and will not be able to converge or provide a meaningful answer. But nonetheless, in all cases, the framework resulted to be quite useful in improving the overall, improving the code quality overall. Now let's take a look at the VHDL version. In this case, things are quite different in some with some models, especially the Llama 370B, which is basically not capable of generating any VHDL that is syntactically correct. So you should be able to see here there is a very small bar here that indicates a 1% more or less success rate for VHDL. And translated to the functional passive one, that means 0%. So none of the 156 benchmarks were correct from the functional perspective. Despite this, by using a framework like ours, we were able to boost the syntax efficiency to almost 60%, and 32% was achieved for the functional correctness. So again, in this case, even if the model, even if Llama 3 was not actually well performing with VHDL out of the box, but just enabling this chain of thought mechanism with the possibility of interacting with external tools, did effective boost up the efficiency of the overall system. So to summarize, almost 100% was achieved in every single syntax-related case. Significant improvement, probably the one with Llama 3, where from 1% we boost up to 60% in the case of VHDL. For the functional, the improvements are, let's say, marginal, okay, with respect to some of the baselines, because there are some baseline models that were released recently that are becoming quite good at understanding the functionality of the design. So trying to produce something that makes more sense when compared to the original requirements. But in any case, open source models most of the time are struggling to convey the right implementation. And the most extreme example is the one with VHDL using Llama 3.370B that goes from 0% basically to a much higher percentage. So the average latency is 42 seconds average. And if we think about it, it's probably a good trade-off, because it means that you can still get something that is much better than what a baseline can produce, but still you would just need a reduced amount of time to just get that done. Again, in this case, this is breakdown of the execution times, basically. So again, you have the models on the x-axis and the latency on the y-axis. What you see here is that in every case, of course, you have much larger latency. That makes sense because you have multiple iterations inside of each loop. What makes the discussion more interesting is probably where this latency is added. So we have, for instance, the biggest gap here with Llama 370B. And this is because Llama 3 is struggling a little bit in generating VHDL. it does indeed require multiple runs to just converge towards a solution. So where in this case was actually on average almost 3.5 iterations per design, whereas in most other cases, 1 or 2 iterations were fine. And the other thing that is interesting is the latency introduced by Claude when working on VHDL. So in this case, you have the largest latency for a specific language. And this is probably due to the fact that instructing and fixing mistakes in VHDL are more challenging for some of those models, probably because of how the model were trained. So probably the scarcity of the data played a role in this case. So some comparison with the state of the art. So of course, there are few other works that are showing something that is similar to this. For instance, RTL Fixer was probably one of the first released earlier this year by NVIDIA. And the important thing of this plot is probably the fact that I'm mixing up frameworks with fine-tuned LLMs. Because the point is, probably it does make more sense to have a framework that does work like what I just showed you, rather than just focusing on fine-tuning or even training an LLM from scratch. For instance, you can see CodeGen. Okay, CodeGen 16B is fine-tuned on a specific language. First of all, you have the problem of the language, which one you will choose. Most of the time, you see fine-tuned LLMs for Verilog, but then in that case, you have no coverage of VHDL. Plus, it's not that easy because at the end of the day, even if you introduce some fine-tuning, you have a big responsibility in making sure that all the knowledge of the model is not messed up, which is not that easy to do as well. In contrast, what you have on the other side is that, and I'm referring to these last 3 bars, you have something that is relying on available, off the shelf, basically LLMs that just gets plugged in inside an optimization loop and that can produce some better results with respect to some fine tuning. So some conclusions. So this 2-stage pipeline workflow seems to be working quite effectively, even when compared to other works. And this is, I mentioned that at the beginning, so I will mention that again. This is April 2, which is basically the second iteration of our framework that was introduced in September. And with these changes to the workflow, we were able to achieve 15% better performance on Verilog alone. Of course, April 2 are just probably some recipes. Okay, you can call it recipes because you are putting together a bunch of models, a bunch of tools in a specific way such that they communicate with one another. But maybe there are other implementations that are even better, probably, that just needs to be tested. Of course, starting from scratch every time is quite challenging. So the idea was, let's try to introduce something that is useful to everybody. So we would like to enable some broader innovation, and I'm taking the chance here to just introduce a Python package that we developed called Nexus. It is open source, and it does facilitate the design of multi-agent system, especially for hardware engineering tasks, which basically means that, well, you can carry out basically every task that you like, but it is specifically designed for hardware engineering because it does allow you to inject some EDA tool information very easily. So the project is open source, so you can go check it out on GitHub. And the package is also available via pip, so you can pip install it and use it right away. Before concluding the presentation, I would like to just show you what this framework can accomplish. So this is a very short demo video. What we are seeing here is not necessarily Nexus as you will see when you access the repo, but it's just an application built on top of it. So it's a Streamlit application built on top of it, just to showcase a little bit what you can achieve with this. And let's just start with the video. So what happens here is that the user is asking. So he's just asking for some specific design done in a specific way. And what we see here, we have some different icons for each and every step. So what we are seeing here is basically the perspective of the supervisor. So the architecture entails code agent, review agent. You can create your own personal agent as well. But in all implementation, you will have a supervisor that does coordinate everything. So what we are seeing here is that the supervisor is thinking about, okay, what I should do based on the requirements. And then it just starts thinking about, okay, let's ask the planner will just devise all the details of the design, what it should be done, essentially. And this is the thought process that comes out of this query. Then the supervisor does ping the code agent to just leverage the planner instructions to just generate some code that makes more sense and is correct right away, potentially. So it does generate the RTL, does generate the test bench, and it also provides some instructions to just verify the design, because as we said before, we would like to have something that is consistent. So we would like to obtain the same result every time, potentially. So what happens here is that, and you see that on the right of the window, you have the agent that does actually convey these commands to the terminal. And as you see here, is just using the terminal to just run iverilog for checking the syntax and simulating the design. And at the end, it will also show the waveforms to the user to just, let people double check everything. The simulation logs here. And then right now we should be able to see the GTK wave window where the user can further interact with the results of the simulation and make sure that everything is in line, or possibly inspect additional carry out some additional inspections to the output. So this is the message exchanged between the debugger to the supervisor, and it just wraps up the simulation, basic results, what was the final outcome, and then what we see here is the response of the supervisor or basically the entire flow to the user, which just summarizes what happened and does provide the information. Source code is generated on the local system, so the user has already access to that. So the only part of the answer that matters to the user is the explanation of what happened. So again, I'm just showing again the URL of the GitHub repo and the source of the package for installation if you want to use pip. And that basically wraps up the presentation. I would like to thank all my colleagues. Thank you very much. If you have any questions.